Before the universe learned how to exist, there was no darkness to break, no silence to echo through space. There was not even emptiness. Space itself had not yet been born, and time had no direction to flow. In that unknowable state, there were no distances to cross, no moments to count, no laws to govern anything at all. What remained was not nothing in the ordinary sense, but a profound absence, an edge where human language collapses and meaning dissolves. Every star that burns, every atom that vibrates, every memory ever formed can be traced backward, toward that boundary. Modern cosmology follows this trail with extraordinary precision, reconstructing the universe's past through ancient light, equations, and cosmic echoes. It can describe the universe when it was younger than a heartbeat, hotter than any star, denser than imagination allows. And yet, at a certain point, the story stops. The equations fall silent. Time itself seems to vanish. This is the paradox that sits at the heart of existence. How can something begin if there is no before for it to emerge from? If time itself came into being, what meaning does causality have at that threshold? Einstein's space-time bends and stretches under the weight of this question, while quantum theory dissolves certainty into probability. Together, they point toward a moment where reality no longer obeys the rules that define it today. Standing at this edge, science does not find an answer, only a question of overwhelming scale. Was the universe born from absolute nothingness, from an eternal state beyond time, or from a deeper reality so unfamiliar that human intuition cannot survive its implications? This documentary begins there, at the fragile boundary where existence itself first dared to happen, and where the greatest mystery of all still waits. At the dawn of the 20th century, the universe still appeared timeless. The night sky suggested permanent stars fixed in place, galaxies suspended like lanterns on an infinite ceiling. For centuries, astronomy had mapped motions within the heavens, but the heavens themselves seemed unchanged. The prevailing belief among scientists was simple and comforting. The universe had always existed, and it would continue to exist forever, unaltered in its grandest form. This assumption began to fracture quietly, not through philosophy, but through observation. In the early 1900s, astronomers turned increasingly powerful telescopes toward faint, spiral-shaped smudges scattered across the sky. These objects were once thought to be clouds of gas within the Milky Way. But as instrumentation improved, it became clear that these spirals were something far more distant, entire galaxies, each containing billions of stars. Humanity's cosmic horizon expanded overnight, and with it came the first hints that the universe was not as still as it appeared. Edwin Hubble, working at the Mount Wilson Observatory in California, was not searching for the universe's origin. His goal was more modest: to measure distances. By studying Kifid variable stars, pulsating stars, whose brightness revealed their true distance, Hubble was able to determine how far away these galaxies truly were. But alongside distance came another measurement, drawn from the subtle shifting of light itself. When light travels through space, its wavelength can stretch or compress depending on motion. If an object moves away, its light shifts toward the red end of the spectrum, a phenomenon known as redshift. When Hubble compared the redshift of distant galaxies to their measured distances, a pattern emerged with unsettling clarity. The farther a galaxy was, the faster it appeared to be moving away. The universe was expanding. This was not a local motion or a temporary fluctuation. It was universal, uniform, and relentless. Space itself was stretching, carrying galaxies apart, not because they were racing through space, but because space was growing between them. The implication was profound. If the universe was expanding today, then in the past it must have been smaller, denser, hotter, younger. This realization alone unsettled the foundations of cosmology. But it raised an even more radical possibility. If expansion were traced backward far enough, all matter and energy would converge toward a single compact state, a beginning. While Hubble provided the observational evidence, the theoretical leap came from an unexpected source. Georges Lemaître, a Belgian physicist and Catholic priest, approached the expanding universe not as a philosophical puzzle, but as a mathematical consequence of Einstein's equations. Einstein's general theory of relativity, published in 1915, described gravity not as a force, but as the curvature of space-time itself. When applied to the universe as a whole, these equations did not favor stillness. They allowed for motion, expansion, and collapse. Lemaitre took these equations seriously. In 1927, he proposed that the expanding universe implied an origin, a moment when all matter and energy were compressed into an unimaginably dense state he called the primeval atom. This was not an explosion in space, but an expansion of space itself from an initial condition beyond ordinary description. The idea challenged centuries of belief in a static cosmos and met resistance from many corners of the scientific world. Even Einstein himself was uneasy. Though his equations permitted expansion, he famously introduced the cosmological constant to force the universe into a static solution, later calling it his greatest blunder. The notion that the universe had a beginning seemed unscientific to some, uncomfortably close to metaphysical creation, but mathematics remained indifferent to discomfort. As observational data accumulated, the expanding universe became impossible to deny. Yet expansion alone did not prove a beginning. A universe could, in principle, expand forever from an eternal past. What science needed was a fossil direct evidence that the universe had once existed in a radically different state. That evidence arrived quietly. Through noise in 1964, engineers Arno Penzias and Robert Wilson were working at Bell Laboratories in New Jersey, calibrating a microwave antenna originally designed for satellite communication. They encountered a persistent background hiss that refused to disappear. It was uniform, coming from every direction, unaffected by time of day or season. They cleaned the antenna, removed sources of interference, even cleared out nesting pigeons, yet the signal remained. Unbeknownst to them, theorists had predicted precisely such a signal years earlier. If the universe began in a hot, dense state, then as it expanded and cooled, it would leave behind a faint afterglow radiation stretched by cosmic expansion into the microwave range. This radiation would not come from stars or galaxies, but from the universe itself, a relic of its earliest moments. The cosmic microwave background. When Penzias and Wilson's measurements were compared with these predictions, the match was extraordinary. The signal represented light released roughly 380,000 years after the universe's birth. When matter cooled enough for atoms to form and photons could finally travel freely, it was the oldest light ever observed, a snapshot of the universe when it was still an infant. With that discovery, the universe acquired a memory. This radiation was not localized. It filled all of space, perfectly uniform to 1 part in 100,000. It confirmed that the universe was once hot, dense, and rapidly evolving. The Big Bang was no longer a speculative model, it was immeasurable reality. The emotional impact of this realization rippled through science. The universe was not eternal and unchanging. It had a history. It had phases, transitions, and a measurable age. Time itself became a cosmic dimension with a starting point written into the fabric of space. As technology advanced, satellites like COBE, WMAP, and later Planck refined these measurements, mapping tiny fluctuations in the cosmic microwave background. These variations revealed the seeds of all future structured regions, where matter would eventually collapse into galaxies, stars, and planets. From subtle ripples in ancient light, the entire cosmic web could be reconstructed. Light became a time machine by observing distant objects. Astronomers were no longer merely looking across space, they were looking back in time. Every photon carried a time stamp. The farther the light had traveled, the younger the universe appeared. Galaxies were seen not as they are, but as they once were, evolving through cosmic epochs. The universe revealed itself as a dynamic process, unfolding over billions of years. This was not a single discovery, but a convergence. Expansion, theory, background radiation, structure formation all pointed to the same conclusion. The universe emerged from an early state radically different from the present. It was smaller, hotter, and denser. Governed by physical conditions far removed from everyday experience. Yet even as this picture solidified, a boundary remained. Science could describe the universe back to a fraction of a second after its birth, when known particles and forces began to take shape. But beyond that, certainty dissolved. The equations of relativity led to infinite density. Quantum theory resisted such infinities. The closer science moved toward the beginning, the more fragile its descriptions became. The discovery phase did not end with answers. It ended with a deeper sense of wonder. Humanity had uncovered evidence that existence itself had a timeline, that the cosmos was not a static backdrop, but a story with a measurable past. And yet, the opening chapter of that story remained obscured, hidden behind a veil where observation faltered and theory strained. What science found was not the beginning itself, but its echo, a whisper carried across billions of years, reminding humanity, younger than time, and that its origin lies just beyond the reach of light. Waiting in silence. For centuries, physics was built on continuity. Motion followed cause, force followed law, and time flowed evenly from an infinite past toward an infinite future. In the universe imagined by Isaac Newton, there was no room for origins. Space was an eternal stage, time an unbroken river. Creation belonged to philosophy or theology, not to equations. Nature, as physics understood it, simply was the idea that the universe itself might have a beginning struck at the heart of this worldview. It was not merely surprising, it was destabilizing. A beginning implied a boundary to explanation, a moment where laws might fail or not yet exist. For scientists trained to believe that nature obeys timeless principles, this was an uncomfortable thought. When Albert Einstein introduced general relativity in 1915, he unknowingly opened the door to this discomfort. His theory replaced Newton's rigid stage with a living geometry, where space and time could stretch, bend, and curve under the influence of matter and energy. Gravity was no longer a force acting within space, it was the shape of space-time itself. The equations were elegant, precise, and deeply unsettling in their implications, applied to the universe as a whole. General relativity did not prefer stillness. It allowed expansion and contraction, growth and collapse. Yet Einstein himself recoiled from what his equations suggested. A dynamic universe implied change on the largest possible scale, and change hinted at a beginning or an end. To avoid this, Einstein introduced the cosmological constant, a mathematical term designed to counteract gravity and hold the universe in a delicate, eternal balance. It was a choice motivated not by data, but by belief. The universe, Einstein felt, should be eternal. As observations mounted and expansion became undeniable, this resistance collapsed. Einstein later abandoned the cosmological constant, but the shock remained. The equations of general relativity, taken at face value, led to an extraordinary conclusion. If the universe is expanding today, then tracing that expansion backward in time leads to a moment when distances shrink to zero. Densities rise without bound, and temperature becomes infinite, a singularity in mathematics. A singularity is not an object, it is a warning. It marks the point where equations no longer yield meaningful answers. In the context of cosmology, singularity represents a state where space-time itself collapses into an undefined condition. Volume vanishes. Curvature diverges. The very fabric that allows events to occur ceases to function. This was not just a theoretical curiosity. In the 1960s, Stephen Hawking and Roger Penrose formalized this conclusion through their singularity theorems. Using general relativity and minimal assumptions about matter and energy, they demonstrated that a universe like ours expanding and obeying known physical conditions inevitably leads to a singularity in its past. The beginning was not an optional interpretation. It was a mathematical consequence. And yet, this consequence was deeply troubling at the singularity. General relativity predicts infinite density and infinite curvature. Quantum mechanics, the framework governing the behavior of particles and fields, cannot operate under such conditions. Its equations rely on finite values and well-defined probabilities. At infinite density, probability dissolves. Measurement loses meaning. Cause and effect blur. This is where physics fractures. Gravity dominates at cosmic scales. Quantum mechanics rules the microscopic. For most of the universe's history, the two coexist peacefully, each governing its domain. But at the singularity, they collide. Neither theory can fully describe what happens. Together, they fail. This failure is not subtle. It is absolute. The singularity is not a place where physics reaches an answer. It is where physics stops asking questions it knows how to phrase. The laws that describe stars, galaxies, atoms, and light cannot cross this threshold. They point toward it, converge upon it, and then fall silent. The shock of this realization runs deeper than mathematics. If time itself begins at the singularity, then the concept of before becomes meaningless. There is no earlier moment, no preceding state, no prior cause. The familiar chain of causalities has happened because that happen breaks down entirely in everyday experience. Beginnings always emerge from something else. A flame begins from a spark. A storm begins from shifting air. A life begins from another life. But the universe offers no such comfort. Its beginning, if described by a singularity, has no precursor within time. It is not an event in time. It is the emergence of time. This idea unsettles intuition at its core. Philosophically, challenges the notion that reality must be explainable in linear terms. Scientifically, it suggests that the deepest questions about existence may lie beyond the reach of current frameworks. Even as cosmology achieved extraordinary success, mapping the universe's expansion, measuring its age, tracing its evolution, the origin itself remained inaccessible. Science could approach the beginning arbitrarily closely. It could describe the universe when it was a second old, a millisecond old, a trillionth of a second old. But the first instant, the boundary where time itself begins, remained unreachable. This proximity without access intensified the mystery. The closer physics moved toward the beginning, the stranger reality became. Temperatures exceeded trillions of degrees. Particles flickered in and out of existence. Forces that are distinct today, gravity, electromagnetism, the nuclear interactions merged into unified states. Symmetries broke. Space itself behaved less like a smooth continuum and more like a restless quantum field. And still, beyond that, the equations failed. This was not a gap caused by lack of data or insufficient technology. It was a conceptual boundary. No telescope could see beyond it. No detector could probe earlier than the birth of space-time itself. The universe had placed a limit on knowability, written directly into its structure. For many physicists, this was intolerable. Science, by its nature, seeks explanation, not surrender. The singularity was seen not as a final answer, but as evidence that existing theories were incomplete. Somewhere beyond general relativity and quantum mechanics lay a deeper framework, a theory of quantum gravity that could describe the earliest moments without collapsing into infinities. Yet such a theory remains. Elusive string theory, loop quantum gravity, and other approaches attempt to reconcile gravity with quantum principles, suggesting that space-time itself may be quantized, composed of discrete units rather than a smooth continuum. In these models, the singularity may be avoided, replaced by a finite, though extreme, state. But without experimental confirmation, these ideas remain speculative. Hovering at the edge of mathematics and philosophy, the scientific shock, then, is not merely that the universe had a beginning. It is that the beginning resists comprehension. It exposes the limits of reductionism, the idea that reality can always be understood by breaking it into smaller pieces and tracing causes backward. Here, there is no smaller piece, no earlier cause. Time, the dimension that orders all events, emerges from this boundary. Space, the arena of existence, unfolds from it. Laws of physics, which govern all change, may themselves arise alongside the universe rather than preceding it. This reverses the usual hierarchy. Instead of laws shaping the universe may shape its laws. The tension lies in what this implies about explanation itself. If the universe has a beginning that cannot be explained by prior physical causes, then some questions may not have answers in the traditional sense. They may describe conditions of possibility rather than events within a system. Science, accustomed to continuity, finds itself confronting discontinuity. And yet, this confrontation is not a failure, it is a revelation. It reveals that the universe is not obligated to conform to human intuition. It reveals that reality may be deeper than the frameworks used to describe it. And it reveals that the origin of everything is not merely a scientific problem, but a profound conceptual challenge at the edge of the singularity. Physics stands silent, not because it has nothing to say, but because language itself runs out. Equations point inward, collapse, and vanish. Beyond that point lies something real, something that gave rise to all structure, all motion, all time, but whose nature remains hidden. The universe allows itself to be known almost entirely. It permits reconstruction of its history across billions of years. It reveals its composition, its evolution, its fate. And yet, at the most fundamental moment of all, it withholds its secret. The first instant remains untouched. Science stands before it. Armed with mathematics and observation, aware of its proximity and its distance at once. The shock is not that the universe began, but that the moment of beginning may forever remain beyond the reach of explanation. Suspended at the threshold where time itself was born, as the shock of a cosmic beginning settled into acceptance, science did not retreat from the mystery. It moved closer. Step by step, observation by observation. Physicists and astronomers began reconstructing the earliest accessible chapters of the universe's history, not by speculation alone, but by reading the faint signatures still embedded in space itself. The universe, it turned out, had not erased its past. It had preserved it in light, in matter, and in subtle patterns written across the sky. The first path inward led through heat. If the universe had once been smaller and denser, then it must also have been hotter. In those earliest moments, temperatures were so extreme that ordinary matter could not exist. Atoms were torn apart, nuclei could not hold together, and even protons and neutrons dissolved into a sea of fundamental particles. As the universe expanded and cooled, it passed through a sequence of transitions, each leaving behind measurable consequences. This cooling history became a timeline, and one of its earliest readable chapters was primordial nucleosynthesis. Primordial nucleosynthesis describes the formation of the universe's first atomic nuclei. Roughly 3 minutes after the Big Bang, the universe cooled enough for protons and neutrons to bind together, forming hydrogen, helium, and trace amounts of lithium. This process depended delicately on temperature, density, and the number of fundamental particles present at the time. Decades later, astronomers measured the abundance of these light elements in ancient gas clouds and distant galaxies. The results were precise and astonishingly consistent with predictions. The universe had followed a script. The observed ratios of hydrogen to helium matched calculations based on a hot, dense early state with remarkable accuracy. This agreement did more than support the Big Bang model. It transformed the early universe into a testable laboratory, one whose conditions could be inferred billions of years later. The first minutes after the beginning were no longer speculative. They were measurable. Yet nucleosynthesis was only a glimpse. To see further back, science needed to observe the universe before atoms existed, before matter became transparent to light. That opportunity arrived through the cosmic microwave background. As the universe expanded and cooled, it reached a critical threshold about 380,000 years after the Big Bang. Electrons combined with nuclei to form neutral atoms, allowing photons to travel freely for the first time. Light, once trapped in an opaque plasma, was released into space. That light has been traveling ever since, stretched by cosmic expansion from visible wavelengths into microwaves. This radiation fills the universe uniformly. It is not emitted by stars or galaxies, but by the universe itself. It is the afterglow of creation. Early measurements revealed the background to be astonishingly smooth, nearly identical in all directions. This uniformity suggested that the early universe was almost perfectly even in temperature and density. But perfection, scientists realized, would be a problem. Without tiny irregularities, matter would never have clumped together to form stars, galaxies, or planets. Structure requires imperfection. To find those imperfections, science turned to precision. In 1989, NASA launched the Cosmic Background Explorer, known as COBE. Its instruments were designed to detect minute variations in the temperature of the cosmic microwave background. For years, the data appeared flat, featureless, uniform. Then finally, the fluctuations emerged differences of only 1 part in 100,000. They were tiny, they were ancient, and they changed everything. These fluctuations represented the earliest imprints of structure in the universe. Slightly denser regions would eventually collapse under gravity, forming galaxies and clusters. Slightly less dense regions would become vast cosmic voids. The entire large-scale structure of the universe was encoded in these faint temperature differences. Cobb's discovery transformed cosmology from theory into precision science. Subsequent missions refined this picture. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, mapped the cosmic microwave background with far greater resolution. It measured not only the size of fluctuations, but their angular distribution across the sky. These patterns revealed the geometry of the universe, confirming that space is nearly flat on large scales. They also provided precise estimates of the universe's age, composition, and expansion rate. Then came Planck. The European Space Agency's Planck satellite, launched in 2009, pushed measurement to its limits. It mapped the background radiation with exquisite sensitivity, resolving subtle features previously invisible. The result was a high-definition image of the infant universe, a portrait of reality when it was less than 1 million years old. From this ancient light, scientists extracted astonishing detail. The universe's age was pinned down to approximately 13.8 billion years. Its composition emerged clearly. Ordinary matter accounts for only a small fraction, while dark matter and dark energy dominate. The initial conditions of the universe appeared simple, smooth, and finely balanced. Too balanced. The deeper scientists looked, the more unsettling the picture became. The early universe appeared remarkably uniform, even across regions that should never have been in causal contact with one another. Light, traveling at finite speed, could not have equilibrated such vast distances in the available time. And yet the cosmic microwave background showed near-perfect uniformity across the entire sky. This became known as the horizon problem. To resolve it, physicists proposed a radical idea: cosmic inflation. Inflation suggests that in the earliest fraction of a second after the Big Bang, the universe underwent an explosive period of accelerated expansion. Space itself expanded faster than light, not violating relativity, because nothing moved through space faster than light. Space itself stretched. In this scenario, regions once microscopically close were rapidly driven far apart. Uniformity was established before inflation, then magnified to cosmic scales. Quantum fluctuations, tiny and unavoidable at microscopic levels, were stretched into the seeds of galaxies. Inflation explained much. It accounted for uniformity, flatness, and the origin of structure. It fit the data remarkably well, and yet it raised new questions. Inflation requires specific conditions to begin. It depends on fields, energies, and parameters that themselves demand explanation. Why did inflation start? Why did it stop? Why did it produce the precise spectrum of fluctuations observed? And most unsettling of all, what existed before inflation? The deeper investigation had not simplified the mystery. It had sharpened it. Large-scale structure mapping extended this tension. Surveys of galaxies revealed an intricate cosmic web with filaments, clusters, and voids spanning hundreds of millions of light-years. Simulations showed that this structure grew naturally from the tiny fluctuations seen in the cosmic microwave background. Gravity amplified small differences over billions of years, sculpting the universe into its present form. This success reinforced the idea that the universe's large-scale features were determined by its earliest conditions. Everything followed from those initial patterns, which made those patterns all the more important. Planck's data revealed that the early universe was not chaotic, but exquisitely simple. The distribution of fluctuations followed nearly perfect statistical rules. Deviations were minimal. Parameters appeared finely tuned. Small changes in initial conditions would have produced a radically different universe, one without stars, without galaxies, without chemistry. This apparent fine balance intensified curiosity about what preceded the observable beginning. Was this balance inevitable or accidental? Was it selected from many possibilities or determined by deeper laws? Did the universe begin in the simplest possible state? Or was simplicity the result of processes still unknown? Each measurement answered one question and raised several more. Quantum fluctuations, once thought to be mere noise, emerged as fundamental. In inflationary models, these fluctuations are unavoidable consequences of quantum mechanics operating in an expanding spacetime. They are random, yet statistically constrained. From randomness, structure emerged. From uncertainty, order grew. This blurred the boundary between chance and necessity. The investigation also revealed limits. The cosmic microwave background represents the earliest light that can be observed. Before that, the universe was opaque. No electromagnetic signal can carry information from earlier times. Gravitational waves, in principle, could penetrate deeper, but their detection remains extraordinarily difficult. Thus, the early universe is studied indirectly through patterns imprinted later. Science infers rather than observes, reconstructs rather than witnesses, and still, the closer cosmology approaches the beginning, the more the universe appears poised at a knife's edge. Slight changes in expansion rate, particle masses, or energy densities would have rendered the universe lifeless. The laws of physics appear stable across time, yet their values seem curiously well-suited to complexity. Some physicists interpret this as evidence of deeper necessity, known principles that fix these values uniquely. Others consider more speculative explanations, such as the possibility that many universes exist, each with different initial conditions, and that observers arise only where conditions permit. But these ideas, while mathematically motivated, remain beyond direct test. What the deeper investigation reveals most clearly is not certainty, but coherence. The universe behaves as if its earliest moments were governed by simple rules, applied with extraordinary consistency. Light, matter, and geometry align in a single narrative, stretching back nearly to the beginning. Yet the beginning itself remains just out of reach. The universe offers its afterglow, its elemental ratios, its cosmic architecture. It allows reconstruction of its infancy with breathtaking precision. But when science attempts to step beyond to ask why these conditions existed at all, it encounters silence. Not the silence of ignorance, but the silence of boundaries. The deeper scientists peer into the past, the more the universe resembles a carefully composed opening movement, one that sets the tone for everything that follows, yet withholds its own origin. The initial conditions appear neither random nor fully explained. Balance between chaos and order, simplicity and complexity. This balance does not resolve the mystery. It intensifies it. The investigation leaves cosmology standing before a question that grows sharper with every advance. If the universe began in such a precise state, what shaped that beginning? Was it the outcome of deeper physical law, the result of quantum inevitability, or the trace of something beyond current comprehension? The universe has revealed its early chapters in light and structure. It has allowed science to map its childhood with extraordinary clarity. And yet, as the investigation deepens, the first page remains unread, present, implied. But unopened, what preceded the beginning remains hidden, not behind ignorance, but behind the very success of discovery itself. As cosmology pressed closer to the origin, clarity did not bring comfort. It brought unease. Each layer of understanding stripped away revealed not a foundation, but another boundary one more resistant to explanation than the last. Inflation, once hailed as the missing key to the universe's earliest moments, began to show its limits. It explained the shape of the universe, the uniformity of ancient light, and the seeds of cosmic structure with remarkable success. But success, in this case, only sharpened the question it could not answer. Inflation described what happened after the beginning. It did not explain why it happened at all. The theory proposed that, in the earliest fraction of a second, the universe underwent an extraordinary expansion driven by a high-energy field. Space itself stretched violently, smoothing irregularities and magnifying quantum fluctuations into cosmic-scale features. Yet inflation required an initial state to ignite at a set of conditions already delicately arranged. The mechanism that powered inflation remained hypothetical, and the reason it began, rather than never occurring at all, remained unknown. This absence was not a minor gap. It was structural. Inflation did not remove the singularity. It postponed confrontation with it. When equations were extended backward beyond inflation, space-time still collapsed toward a boundary where known laws dissolved. The universe, even in its most sophisticated models, still pointed inward toward a moment where explanation ended. At that boundary lies the Planck scale. The Planck time approximately 10 to the minus 43 seconds after the beginning marks. The smallest interval of time for which current physics retains meaning. It is derived from fundamental constants: the speed of light, the gravitational constant, and Planck's constant. Below this scale, space-time itself is expected to behave in unfamiliar ways. Quantum fluctuations become so intense that geometry may lose coherence. Distance and duration cease to be well defined. This is not merely a technical limitation, it is a conceptual horizon. Beyond the Planck time, there are no tested equations, no observations, no established framework. Physics, as currently known, does not describe what happens there. The universe in its earliest instant may not resemble anything recognizable as space or time. It may be governed by principles not yet discovered or not discoverable at all. This realization deepens the mystery into something more unsettling than ignorance. It suggests that the origin of the universe may be fundamentally inaccessible, not because technology is insufficient, but because reality itself conceals that threshold. Science encounters a wall not of distance, but of meaning. As cosmology advanced, the questions grew heavier. Did the laws of physics exist before the universe, or did they emerge alongside it? If laws govern reality, what governed the emergence of laws themselves? In everyday experience, rules precede outcomes. But at the beginning of everything, this order may reverse. Some physicists argue that the laws of physics are timeless, existing independently of the universe they describe. Others suggest they are emergent products of symmetry breaking, phase transitions, or deeper mathematical structures that only become meaningful once the universe exists. In this view, laws are not imposed on the universe. They crystallize within it. This distinction is not philosophical decoration. It reshapes the nature of explanation. If laws pre-exist the universe, then the beginning might be governed by necessity. If laws emerge with the universe, then the beginning may be contingent, one possibility among many. Either way, the question refuses closure. Even time itself becomes uncertain. In classical thinking, time flows independently of events. In relativity, time is bound to space, shaped by matter and energy. Near the beginning, when density approaches infinity, time may lose its direction. Some models suggest that time behaves like a spatial dimension near the origin, smoothing the singularity into a boundary without edges. Others propose that time emerges from more fundamental processes, arising only after certain conditions are met. If time is emergent, then the phrase "before the universe" loses meaning. There is no earlier state, no prior moment, no hidden prehistory waiting to be uncovered. The universe does not begin within time. Time begins within the universe. This inversion unsettles causality itself. Cause and effect require temporal order. Without time, causation dissolves. The universe's origin may not be something caused in the usual sense. It may be a boundary condition of fact rather than an event. Physics is accustomed to tracing effects backward to causes. Here, it encounters something that may simply be. This realization fuels deeper paradoxes. If the universe has a beginning, what determines its initial conditions? Why these values and not others? Why a universe that permits structure, chemistry, and complexity? The early universe appears balanced with extraordinary precision. Small deviations in expansion rate, particle masses, or force strengths would have rendered it sterile or chaotic. The origin seems delicately poised. Some interpret this as evidence of underlying necessity, hidden principles that fix these values uniquely. Others consider the possibility that many universes exist, each with different initial conditions, and that observers arise only where conditions permit. In such scenarios, the universe's apparent fine balance is not explained by design but by selection. Yet even this does not dissolve the mystery. It relocates it. If there are many universes, what mechanism generates them? What governs their properties? What exists beyond them? The question of origin expands rather than contracts, pushing explanation further away. The idea that the beginning might be a transition rather than a creation adds another layer. Some models propose that the universe emerged from a prior static contracting phase, a quantum vacuum, or a timeless background governed by unfamiliar rules. In these scenarios, the Big Bang is not the absolute beginning, but a transformation of phase change in a deeper reality. But such models still confront the same boundary. They must explain the conditions that allowed transition to occur. They must account for why one phase gives rise to another. They do not eliminate the question of origin. They shift it. The escalation lies in recognizing that no matter how refined the theory, the origin recedes. Each advance in cosmology narrows uncertainty in one direction while widening it in another. The universe's history becomes clearer, its structure more precise, its evolution more predictable. And yet, the first instant remains opaque, protected by the very laws that make understanding possible. This is not failure. It is a revelation of scale. The universe allows inquiry into its behavior across billions of years and trillions of kilometers. It permits reconstruction of its infancy through light and mathematics, but it may not permit access to its absolute origin. The boundary at the beginning may be woven into reality itself, a limit not of human ingenuity, but of nature's openness. This possibility is unsettling because it challenges the expectation that all things must be explainable. Science is built on the premise that deeper understanding awaits with deeper investigation. Here, that premise trembles. The origin may be real, but unreachable. Not hidden in distant space, but sealed in conceptual depth. At this point, the mystery is no longer merely scientific. It becomes existential. If the universe's origin cannot be explained by causes within time, then existence itself may rest on something that cannot be reduced, predicted, or derived. Reality may contain facts that simply are. This does not diminish science. It sharpens its role. Science becomes not a conqueror of mystery, but its cartographer. It maps the boundary, traces its contours, and identifies where explanation ends. The escalation of mystery does not close inquiry, it reframes it. The closer cosmology moves toward the beginning, the more it encounters questions that do not behave like ordinary problems. They do not yield to improved instruments or refined equations. They persist because they are about the conditions under which explanation itself becomes possible. At the edge of the Planck time, space-time dissolves into uncertainty. At the edge of causality, sequence collapses. At the edge of law, order gives way to emergence. These edges do not point to ignorance. They point to structure at a deeper level. The universe may not hide its origin out of indifference, but because the origin is not something that can be revealed in the usual way, it may be less like an event to be observed and more like a boundary to be. Acknowledge this realization deepens the mystery beyond. Fear into awe. The escalation is complete when science recognizes that it may be standing before something ultimate, not a thing, not a cause, but a limit. A place where explanation stops not because it has failed, but because it has reached the deepest layer accessible to it. The universe does not answer the question of its own beginning. It simply exists, and in doing so, it invites a humility as vast as the cosmos itself. When explanation reaches its limits, imagination does not replace science, it extends it. Faced with a beginning that resists direct description, physicists have not abandoned rigor. Instead, they have turned to theories that stretch known laws to their edge, asking not what happened before the universe, but what the word before could possibly mean when time itself is part of the phenomenon under study. These theories do not claim certainty. They offer structured ways to think where intuition fails. Using mathematics as a lantern in conceptual darkness, one of the most influential attempts to soften the singularity came from Stephen Hawking and James Hartle. Their no-boundary proposal begins with a subtle but radical shift in perspective. Near the origin of the universe, they suggested time may behave less like a flowing dimension and more like a spatial one. In ordinary experience, space has no preferred direction. North is not more fundamental than south. By contrast, time appears directional, always moving forward. But near the beginning, Hawking and Hartle proposed this distinction may dissolve. In their model, the universe does not begin at a sharp edge. Instead, space-time curves smoothly, like the surface of a sphere. A sphere has no boundary. It does not begin or end at any point, yet it is finite. Similarly, the universe could be finite in time without requiring a singular starting moment. There is no instant where time suddenly appears. Rather, time gradually acquires direction as the universe expands and cools. In this view, it's asking what came before the universe is like asking what lies south of the South Pole. The question itself loses meaning. There is no earlier moment, not because it is hidden, but because the structure of space-time does not allow it. The no-boundary proposal does not eliminate mystery, it reframes it. The universe exists without an origin in the traditional sense, yet remains fully described by physical law. This idea does not rest on metaphor alone. It emerges from applying quantum mechanics to gravity, treating the universe itself as a quantum system. While such models are difficult to test, they are mathematically consistent extensions of established theory. They suggest that the singularity is not a physical point of infinite density, but a sign that classical descriptions have been pushed beyond their domain. Other approaches go further, proposing that the universe emerged through a quantum process similar to those observed at microscopic scales. In quantum mechanics, particles can appear spontaneously from the vacuum, borrowing energy briefly in accordance with uncertainty principles. This vacuum is not emptiness, but a restless state filled with fluctuating fields. Some quantum cosmology models propose that the universe itself could have tunneled, put into existence from such a quantum vacuum. In this picture, there is no classical space-time before the universe. There is only a quantum state, with no geometry, no time, and no classical reality. Through a process governed by probability rather than causation, space-time emerges. This tunneling does not occur in time. Time emerges with it. The universe, in these models, is not caused in the usual sense. It is a quantum event governed by statistical likelihood rather than deterministic sequence. The beginning is not an explosion from nothing, but a transition from a non-classical state into one where space and time become meaningful concepts. These ideas remain speculative, yet they are anchored in well-tested principles. Quantum tunneling is observed routinely in particle physics. Vacuum fluctuations are measurable. What changes is scale, not mechanism. The challenge lies in extending these principles to the universe as a whole. Another family of theories challenges the assumption that the Big Bang was the absolute beginning at all. Cyclic and bouncing universe models suggest that the universe may undergo repeated phases of expansion and contraction. In these scenarios, the Big Bang marks not creation, but transformation. In a bouncing universe, a prior cosmic phase collapses under gravity until extreme density is reached. Instead of forming a singularity, quantum gravitational effects become dominant, generating a rebound, a bounce that initiates a new expansion. The universe emerges from its own past, reshaped but continuous. Such models attempt to resolve the singularity problem by replacing infinite density with a finite maximum. Time does not end at the Big Bang. It passes through it. The beginning becomes a bridge rather than a wall. Some versions of cyclic cosmology, inspired by string theory, envision an endless sequence of universes, each born from the death of the previous one. Expansion stretches spacetime, diluting matter and energy until conditions resemble emptiness. Then, through mechanisms not yet fully understood, contraction begins anew. These ideas are mathematically sophisticated and deeply constrained by observation. They must reproduce the precise patterns seen in the cosmic microwave background, the abundance of elements, and the large-scale structure of the universe. So far, no cyclic model has decisively replaced inflation, but none have been ruled out entirely. Their appeal lies not in certainty, but in continuity. They offer a universe without an absolute beginning, where time extends indefinitely and creation is replaced by renewal. Yet even here, the question of origin persists. If the universe cycles eternally, what governs the cycle itself? Why these laws, this structure, this rhythm? The mystery does not vanish, it recedes. Beyond these models lies a more expansive possibility, the multiverse. Inflationary theory, when examined closely, suggests that inflation may not occur once, but repeatedly. In some versions, inflation never completely ends. Instead, it continues in different regions of spacetime, spawning distinct universes with varying properties. Our observable universe would be one such region, a bubble in a far larger cosmic foam. In this picture, the Big Bang is not the beginning of everything, but the beginning of our local spacetime. Other universes may have different physical constants, different dimensions, even different laws. The apparent fine balance of our universe becomes a selection effect. Only universes with stable conditions can host observers, capable of asking questions. The multiverse does not arise from speculation alone. It emerges naturally from certain solutions to inflationary equations and from aspects of string theory, which permits an enormous number of possible vacuum states. Each vacuum corresponds to a different set of physical laws. Yet the multiverse remains controversial. It's not because it is fantastical, but because it is difficult to test. If other universes exist beyond our cosmic horizon, their influence on ours may be subtle or non-existent. Science, which depends on observation and falsifiability, approaches this idea cautiously. Still, the multiverse reframes the origin question in a profound way. If many universes exist, then the origin of our universe may not be unique. The deeper question becomes the origin of the multiverse itself, the framework that allows universes to form at all. Once again, explanation expands rather than concludes. Across all these theories, no boundary models. Quantum tunneling, bouncing cosmologies, and multiverses, a common theme emerges. None describe a simple beginning in time preceded by another time. All suggest that the concept of before breaks down at the deepest level. Time may curve. It may emerge. It may cycle. It may fragment across multiple realities. But in no case does it behave as ordinary intuition expects. These theories do not claim to reveal what happened before the universe. They challenge whether such a question is even coherent. They replace linear narratives with geometric ones, deterministic causes with probabilistic transitions, singular moments with extended structures. Importantly, they remain grounded in mathematics and known physics. Each proposal is constrained by equations that reduce to established theories under familiar conditions. They are not stories invented to fill ignorance, disciplined attempts to follow logic beyond the limits of observation. And yet, none are complete. No experiment has yet confirmed quantum gravity. No observation has decisively distinguished between inflationary beginnings and bouncing ones. No signal has revealed other universes. Theories multiply not because science is careless, but because reality allows multiple consistent descriptions at the edge of knowledge. This plurality is not weakness. It is honesty. Science does not claim certainty where evidence is absent. It explores possibilities, tests implications, and refines models. In the face of the universe's origin, it acknowledges that several answers may be mathematically viable. Even if only one corresponds to reality, what unites these theories is not agreement, but humility. They accept that the origin of everything may not resemble any event within the universe. It may not be localized, sequential, or causal in the usual sense. It may be a condition, a structure, or a rule that does not unfold in time, but gives rise to time itself. In this light, the first moment before everything becomes less like a point and more like a question or a question embedded in the fabric of existence. Each theory offers a different way to interpret that question. None dissolve its mystery. All deepen it. The universe, it seems, does not yield its origin easily. It allows itself to be modeled, approximated, and extended through mathematics, but it resists final explanation. Theories circle the beginning, illuminate aspects of it, and then return with more refined uncertainty. This is not the failure of understanding. It is its frontier at the deepest level. Science may not discover what came before the universe, because before may not exist as a category. Instead, it may discover that the universe's origin is not an event hidden in the past, but a boundary condition woven into reality itself. Theories do not close the story. They open it wider, revealing that the question of beginnings is not something to be solved and set aside, but something that accompanies existence wherever it unfolds. And so, the search continues not toward a final answer, but toward a deeper understanding of what it means for anything to begin at all. The universe does not reveal its origin willingly. It does not offer a clear signal or a single decisive experiment. Instead, it leaves traces subtle, dispersed, and ancient embedded in phenomena that persist long after the first moments have passed. Modern science approaches this challenge with patience, not expecting a dramatic unveiling, but engaging in a slow dialogue with reality, listening for whispers rather than proclamations. One of the most promising avenues into the universe's earliest moments lies not in light, but in vibration. Gravitational waves are ripples in space-time itself, produced when massive objects accelerate or collide. Unlike electromagnetic radiation, they do not scatter easily. They pass through matter almost unhindered, carrying information across vast distances and epochs. In principle, gravitational waves generated in the earliest instance of the universe could still be traveling through space today, untouched by the opacity that once trapped light. If cosmic inflation occurred, it should have produced a background of primordial gravitational waves of faint, persistent tremor imprinted into spacetime as it expanded violently. Detecting this signal would not show the beginning directly, but it would offer a glimpse into the physical conditions that shaped it. Observatories such as LIGO and Virgo have already demonstrated the reality of gravitational waves by detecting mergers of black holes and neutron stars. These detections confirm predictions made by Einstein a century earlier, yet the primordial background remains elusive, far weaker than the waves produced by astrophysical events. To search for it, scientists turn to increasingly sensitive instruments and creative strategies. One such strategy involves studying the polarization of the cosmic microwave background. If primordial gravitational waves passed through the early universe, they would have left a distinct twisting pattern known as B-mode polarization. In the ancient light released shortly after the Big Bang, experiments like BICEP, the South Pole Telescope, and future space missions are designed to search for this subtle signature so far. Results remain inconclusive. Signals once thought promising have been traced back to cosmic dust rather than primordial waves. Yet this does not signal failure. It reveals the difficulty of the task. The universe's earliest tremors are faint, buried beneath layers of later activity. Extracting them requires not only sensitivity but restraint. Each non-detection narrows the range of possible theories. Inflation models are refined. Parameters are constrained. Silence itself becomes data. At smaller scales, particle physics offers another route inward. The early universe was an arena of extreme energy, far beyond what can be achieved naturally today. In those conditions, forces that are distinct, now electromagnetic, weak, and strong, may have been unified. Understanding this unification is key to understanding the earliest moments. Particle accelerators, such as the Large Hadron Collider, recreate fragments of these extreme conditions by smashing particles together at high energies. While they cannot reach Planck scale energies, they probe regimes where new physics may emerge. Discoveries like the Higgs boson confirm that fields permeate space and shape the properties of Materan insight with deep cosmological implications. The Higgs field, in particular, may have played a role in the early universe, influencing inflation or phase transitions that shaped spacetime itself. Subtle properties of this field, its stability. Its interactions could hint at whether the universe exists in a stable state or a metastable one. Balanced precariously over deeper possibilities, such questions are not abstract. They connect particle physics to cosmology directly, suggesting that the universe's fate and origin may depend on the same underlying structures. Beyond accelerators, future experiments aim to push further. Proposed colliders, more powerful and precise, seek signs of supersymmetry, extra dimensions, or other extensions of known physics. Each potential discovery would reshape understanding of the early universe, not by revealing its first instant, but by clarifying the rules that governed it. On cosmic scales, new generations of telescopes are extending humanity's reach deeper into space and time. Instruments like the James Webb Space Telescope peer into the era when the first stars and galaxies formed, revealing how structure emerged from initial conditions. By mapping this evolution, cosmologists test models of inflation, dark matter, and cosmic expansion. Large-scale surveys, such as Euclid and the Vera C. Rubin Observatory, aim to chart the distribution of galaxies across enormous volumes of space. Their data will trace the cosmic web with unprecedented resolution, revealing how matter clumped over billions of years. The patterns observed today are fossils of the earliest fluctuations. By measuring them precisely, scientists infer the statistical properties of the universe's birth. These surveys do not seek a single origin event. They seek consistency. They ask whether the universe's structure aligns with predictions made by competing theories. They look for anomalous and unexpected correlations, deviations from symmetry that might signal new physics. At the same time, cosmologists analyze spacetime itself. General relativity predicts that geometry encodes information about energy and matter. Precise measurements of cosmic expansion, gravitational lensing, and spacetime curvature test whether Einstein's equations remain valid under extreme conditions. Deviations could point toward quantum gravity effects, subtle echoes of the universe's earliest state, even neutrinos, nearly massless. Particles that rarely interact with matter are part of this investigation, produced abundantly in the early universe. They carry information about conditions seconds after the Big Bang, detecting and characterizing the cosmic. Neutrino background remains a formidable challenge, but it represents another potential window into primordial physics. Across all these efforts, a common method emerges: inference. The first moment cannot be observed directly. It left no photograph, no single signal that can be isolated and replayed. Instead, it shaped everything that followed. Its influence is distributed across the universe, woven into light, matter, and geometry. Science reconstructs it the way a geologist reconstructs ancient tectonic events by studying the landscape they left behind. This reconstruction is slow. It unfolds over decades, sometimes generations. Instruments are built, data is collected, theories are tested, discarded, refined. Progress does not come as revelation, but as convergence. Multiple lines of evidence begin to point toward the same constraints, narrowing the space of possibilities. Patience is not a virtue here. It is a necessity. The universe operates on timescales that dwarf human experience. Its signals are faint, not because they are insignificant, but because they are ancient. Extracting meaning from them requires humility, discipline, and acceptance of uncertainty. Science acknowledges that some questions may never receive definitive answers, The first moment of the universe may belong to this category. It may be inaccessible not because it is hidden far away, but because it is foundational, because it defines the conditions under which observation itself becomes possible. Yet this does not render the search meaningless. Every constraint placed on inflation, every measurement of cosmic structure, every test of fundamental physics deepens understanding of how the universe behaves near its limits. Even if the origin itself remains unreachable, its influence can be mapped, bounded, and understood indirectly. In this sense, science does not chase an illusion. It traces a shadow. The ongoing testing of theories is not aimed at conquering the mystery, but at respecting it. Models are judged not by their ability to answer everything, but by their consistency with what is known. Speculation is disciplined. Imagination is tethered to mathematics and data. This slow dialogue with nature contrasts sharply with the desire for dramatic answers. There is no final experiment waiting to be switched on, no singular discovery that will dissolve all uncertainty. Instead, there is a steady accumulation of insight, each piece adding texture to the cosmic narrative. The universe responds not to impatience, but to careful listening. As instruments grow more sensitive and theories more refined, science edges closer to the boundary where explanation fades. It does so knowingly, aware that the destination may not be resolution, but understanding of limits. In mapping those limits, science clarifies not only what can be known, but what it means to know it all. The earliest moments of the universe remain silent, yet their echoes persist everywhere in the distribution of galaxies, in the whisper of radiation, in the curvature of space-time. By studying these echoes, science learns not how the universe began, but how it remembers. And in that memory, fragmented and ancient, the universe reveals itself not as a puzzle to be solved, but as a history to be interpreted patiently, carefully, and without expectation of final closure. The search for the universe's beginning leads not to a final answer, but to a quiet reckoning. After equations have been traced to their limits, after light has been followed back across billions of years, what remains is not emptiness, but reflection. Humanity finds itself living inside a universe that appears to have a history, a measurable age, and an unfolding narrative yet whose ultimate origin may resist explanation forever. This realization reshapes the meaning of causality itself. In everyday experience, causes precede effects. Events unfold along a chain that can be followed backwards, step by step, but a universe with a beginning challenges the structure. If time itself emerged with the cosmos, then causality does not extend beyond that emergence. The familiar logic of because dissolves at the edge of time. The universe may not have been caused in the way events within it are caused. Its existence may not be the result of a prior moment, but the condition that allows moments to exist at all. This is not a gap in understanding. It is a transformation of perspective. The universe no longer appears as a machine switched on at a particular instant, but as a reality whose deepest features define the possibility of explanation. Space, time, and law are not external frameworks imposed upon existence. They are part of what existence is. To ask why the universe exists in the same way one asks why a star shines may be to misapply the question itself. Such a conclusion is unsettling, yet profound. For centuries, humanity has sought ultimate explanations, first in myth, then in philosophy, then in science. Each step brought deeper clarity and greater humility. Science revealed that Earth is not the center of the cosmos, that the sun is one star among hundreds of billions, that galaxies themselves are fleeting structures in an expanding universe. The discovery of a cosmic beginning extended this humility further. Existence itself became finite in age, contingent, dynamic, yet the possibility that the beginning has no explanation within time extends humility to its furthest reach. It suggests that reality may not be built upon a final cause that can be uncovered and named. Instead, it may rest upon a boundary one that defines what explanation means, rather than yielding to it. The universe becomes not a solved equation, but an open question, continuously unfolding in this light. The mystery of the first moment is not an obstacle to meaning. It is a source of it. Human understanding has traced the universe's story from the formation of the first atoms to the emergence of stars, planets, life, and consciousness. It has mapped the laws governing matter and energy with extraordinary precision. It has listened to the echo of creation itself in ancient light. And yet, standing at the threshold where time begins, it encounters silence. This silence is not empty. It is full of implication. It reminds humanity that knowledge has horizons, not because nature is hostile to inquiry, but because inquiry is part of nature. The mind that asks questions is itself a product of cosmic evolution. The universe has become aware of itself through beings who can reflect, calculate, and wonder. That awareness does not grant dominion over all mysteries. It grants participation in them. To exist in a universe with a beginning is to exist within a story that did not need an audience to unfold, yet somehow produced one. This realization alters the meaning of existence. Life is no longer a trivial byproduct of matter, nor merely a temporary arrangement of particles. It is part of a long cosmic process that began in conditions unimaginably distant from human experience. Every thought, every question, every act of curiosity is connected through an unbroken chain of physical processes to the earliest moments of reality, yet the origin of that chain may not be traceable. The universe, then, is not a finished answer waiting to be decoded. It is an unfolding question, one that continues to generate structure, complexity, and awareness. Its laws allow prediction, but not closure. Its history can be reconstructed, but not completed. This reframes the role of science itself. Science is not diminished by uncertainty. It is defined by it. Its power lies not in claiming final truths, but in refining understanding, testing limits, mapping the boundaries of the knowable. In confronting the universe's origin, science encounters a question that may never be settled. It remains essential to ask. The inability to explain the first moment is not a failure of reason. It is a reminder that reality is deeper than any single framework. There is a temptation to see mystery as something to be eliminated. But some mysteries endure not because they are unsolved, but because they are fundamental. They are not puzzles missing pieces. They are edges beyond which familiar concepts lose meaning. The origin of the universe may belong to this category. If so, then the absence of an ultimate origin story does not strip the universe of meaning. It enriches it. Meaning no longer comes from a definitive beginning or a predetermined purpose. It arises from participation, from being part of a cosmos that evolves, explores, and reflects upon itself. The universe does not need a narrative justification to exist. It simply does, and within it, meaning emerges through relationships, patterns, and awareness. This perspective invites humility without despair. Humanity stands on a small planet orbiting an ordinary star in a vast galaxy, itself one among trillions. Yet within this modest setting, the universe has produced minds capable of tracing its history almost back to the beginning of time. That achievement is not diminished by the presence of unanswered questions. It is defined by them. The first moment before everything may remain forever beyond reach, not hidden, not erased, but conceptually inaccessible. It may not be something that can be discovered, only something that can be acknowledged. In accepting this, science does not retreat. It clarifies its purpose. The purpose is not to eliminate mystery, but to understand the structure of mystery. At the end of this journey, there is no final revelation. There is no singular explanation that dissolves uncertainty. Instead, there is awe, quiet, expansive, and enduring. Awe at a universe that began, evolved, and gave rise to beings capable of asking how it began at all. The universe does not answer the question of its own origin. It offers something else instead, existence itself, unfolding without obligation to human expectation. And perhaps that is enough. The first moment before everything remains untouched. Not as a flaw in understanding, but as a reminder that reality is deeper than certainty. Science reaches the edge of time, looks into the silence beyond, and does not turn away. It listens. In that listening, meaning does not vanish. It expands. The universe is not finished speaking. It is not finished becoming. And humanity, tracing its history back to the edge of time, is not separate from that process. It is one of its expressions, brief questioning, profoundly aware that some mysteries are not meant to be solved, but to be held in wonder.